and I'm very glad to welcome you all here in the second lecture in our webinar series. And while the first session looked back into the past and explored history, today's lecture will offer an overview of the chemistry of natural dyes. And it will be delivered by Riikka Räisanen, professor at the Department of Education and the University of Helsinki. With a background in chemistry, she has dedicated many years to researching natural dyes and their potential application in the modern world. And she is also the leader of the project Colour4CRAFTS, which is behind this lecture series. And now I am happy to give the word or the stage to Riikka.
Okay, thank you very much. And I will share my screen and hopefully it will be seen by you.
Yes, we can see, but
I try to, yeah, now is it in the presentation mode for you also?
Yes, it's the presentation mode. Perfect.
Okay, so thank you very much, and thank you, Riina, for the introduction, and thanks for the organizers for giving me the opportunity to explain some of the characters of natural dyes. So as you probably know, but human beings have been very fascinated with the colors already very early in history. These are the cave paintings from North Spain from more than 10,000 years back. And already here we can see beautiful red and black colors. Also in the quite early age, the professionals wrote down the dyeing recipes. So in old days, all colorants were obtained from nature, and basically it was 3 colors, blue, red, and yellow, which were mainly then overdyed with each other to complete a set of rainbow colors. And already in the very early age, also the recipes were written down, like here is a Neo-Babylonian writing from 300 BC at the British Museum, which tells us how to dye wool with madder roots. And astonishing is that the recipe that is described in this stone also is very much similar, which has been used centuries later in European and also in our Baltic dyeing recipes. So the good recipes and good methods were already known very early. Crucial thing was in 1856 was the first synthetic dye invented. William Henry Perkin invented Morvein, where he wanted to develop a compound from coal tar towards malaria, so some drug. But he discovered that he created this beautiful violet color liquid and dipped a silk yarn into it and recognized that it dyed the silk very, very brightly and beautifully. So then, and this created the first synthetic dye, and the development of chemistry was actually in early days at the end of 19th century very much on dye chemistry, and already also almost all basic structures of dyes were developed by the end of the 19th century. Then new dyes also were needed because the need for new fibers was essential due to the revolution, industrial revolution, and the expand of population. So synthetic fibers were developed, and therefore also acidic dyes in 1940s to dye polyamide. Later in 1950s, dispersed dyes to dye polyester, and later 1956 reactive dyes for cotton. But anyway, it was already before this 1850s, so old days that people used colorful clothing, and as we can recognize when we look around the nature, that there are a lot of different sources where colorants can be obtained. Plants, berries, flowers, algae, mushrooms, fungi, microbes, so very different sources. Also, we can create the whole rainbow of colors from these natural sources. Colorants are natural colorants come from these living organisms, and colorants are secondary metabolites in these organisms. If you have studied biology or you remember from school, so the secondary metabolite means that it's not important for the vital living of the plant or the organisms, but many times these secondary metabolites have other important roles, like they are involved in reproduction, or very often chemical defense and defense from attacks of microorganisms and animals towards the species. The crucial thing in nature-based products and nature-based compounds is that they are not stable. They are seldom end products of processes. Instead, they continue changing in the new compounds. And this is crucial difference when we compare natural colorants and synthetic colorants, because synthetic colorants are designed to be very stable and such that they don't change during all kind of processes or ultraviolet light or heat. These secondary metabolites, in this case, we look at colorants. So they are synthesized in cytoplasm in a cell. And as we know, all living organisms are about 90% water. So these colorants also need to be very water soluble so that they can be present and not cause harm in these plants. Naturally, there are also some not water soluble, so insoluble or lipid soluble, and those are then stored in these lipid walls or cell walls in plants. But most colorants are very water soluble. They are even connected to sugar, like here is betaine, E162. This is additive, food additive, and food color, this E code. And these important character of these natural colorants is that there are these hydroxyl groups, which you can see in multiple places in this core structure, and they make they are involved in this water solubility, which I will then later tell a little bit more about. What kind of colorants can be found in natural organisms? So you probably know the most known natural colorant, as we think that nature is green, is chlorophyll. Its structure is here, chlorophyll A. It is like a ring structure, and there's magnesium in the middle, and then it has a long tail with this carbon chain at the end. It's present in green leaves, and it is an important compound for the energy production and capturing light. But the bad thing is that it degrades very easily. So actually chlorophyll cannot be used for dyeing. However, some people call this core structure without the tail also as chlorophyll or chlorophyllin, and this part can be extracted, and also this magnesium can be changed, for example, to copper, which makes the structure more stable. And this kind of green colorant, copper chlorophyllin, is used, for example, in toothpastes, which are green. You might know, for example, some Pepsodent type of toothpastes are green. Then there are anthracenones, this kind of three benzene rings together, attached together with hydroxyl groups and these ketone oxygens in the middle. This is alizarin, and alizarin is the main component of madder root. And this kind of anthraquinone compounds create very often red color in textiles, and this kind of colorants are very stable. Therefore, in old textiles, you can very often see red present, like in wall hangings or other textiles, because these are very stable. So red can be obtained from madder root and also some insects like kermes and cochineal. Then we have carotenoids. Here is fucoxanthin, which is found in algae, for example. Also carotenes which are the yellow colorants in carrots, are very bright, create very bright color. But unfortunately, these carrots are lipid soluble. If you have created and boiled carrots in water, like for food or for carrot soup, you can recognize that not so much yellow color is soluble in water. So these carotenoids are not very suitable for dyeing purposes, because we use water for dyeing textiles. But these xanthophyls, which include hydroxyl groups and carboxylic acid groups, which are more make the compound water soluble. So this kind of carotenoids, xanthophyls, can be used in dyeing. A great big group of natural compounds are flavonoids, Here is the structure of luteolin, and these are very much present in almost all green plants and flowers, and it's very diverse group of compounds, but also very much useful for yellow colors in textiles. And then here is indigo, and indigo is one of the blue colorants in nature. So blue color actually is quite rare in natural colorants, but indigo is one of the nature's blue compounds that can be captured in textiles. Of course, if we think of this indigo plant, the plant itself is green, and these indigo colorants are as precursors, colorless precursors in the plant. But when this process of extracting the colorant is used, then this blue indigo appeared during the process. And this extraction process also includes high pH, oxidation, and through this process, then the blue indigo as a pigment, as powder, can be obtained. So here is one example of these hydroxyl groups in compounds. As I told you, so because the colorants need to be water soluble, so they have the hydroxyl groups. And this is an example of aronia, the colorant from aronia berries. This is very common, at least in Finland, I believe also in Estonia. It's used as perennial or herb bushes in parks and gardens, and it makes these very dark, almost black berries, which actually contain also very much vitamin C. But the colorant is this kind of lavulium cation, and in pH 3, so very acidic environment, it's as cation, so plus charge. But when the pH changes, the structure and also the color of this compound changes from this kind of reddish brown color into blue. And here in the above pictures, so you can see the extract of this berry, how the color changes from red into blue. And this blue bear appears in pH 11. And here is absorption then measured from 330 nanometers to over 700 nanometers, and we can see the photochromic shift where the absorption maxima shifts from left to right. And because this color changes during the pH change, so this might then create a slight problems or challenge in washing textiles, because usually when we dye textiles with natural colorants, the pH is acidic, so it's around 3 or 4. In this case, with these aronia berries, the color would be around red. And when we wash the wash the textile with the commercial detergent, the pH is very often quite basic, and the color can turn into blue. So this is something that needs to be taken into account when dyeing with natural dyes. I'm sorry, I think I have something noise coming behind me, so I must.
No, it's okay, at least for me.
Sorry. Okay. Now I think it's better. Then I have here another example. This is red onion peels, and this is the same thing. So there is a quercetin derivative is one of the main colorants. Also this peonidine is present in especially these red onion peels, and there also we see the color change from red into green during the pH change. So pH 1 on the left, pH 11 on the right. Okay, I don't know if you already know probably something about this Colour4CRAFTS research project, but I will shortly explain our aims and what we are doing. So this name comes from color for combining, re-engineering, applying, futuring, transforming, stretching. With these words, we want to say that we study the past, but we want to stretch the limits of natural colorants for the future. The organizing institution is the University of Helsinki. Then we have University of Lapland, University of Tartu, University of Leeds, and then KIK IRPA, Royal Institute of Cultural Heritage from Belgium, and a company, Tilly, from France. So we have quite a multidisciplinary group of researchers in this research project. We have and we used methodologies of history, artifact research, cultural studies, art and craft research, research of natural sciences, and also future studies. And we look the color and coloration skill from tradition to the future. Also, how we can transfer the knowledge. We are preparing an educational guide, which will come out in October this year. I will tell about that a bit later. We want to foster the European cultural heritage, create education, and then provide futures visions for coloration and textile production in Europe in the future. So quite broad perspectives, and we kind of do research on 3 different time scales. So traditional craft in the back in history, creative sector, now what is going on with artisans and craft professionals and craft creators. And then how we can develop new cutting-edge technologies for the future's use. And we also work with this futures cone ideas to look for or to look at these futures possibilities. Here's a little bit shortly how we can study the past techniques and past coloration, and how we can study the future and create new dyings. So here are a few folk costumes from Koivisto, Karelia in Finland. They have a little bit similar features as Estonian folk costumes. Red is very common color. You can see also blue and yellow. So here also we can see the basic colors that can be easily obtained. Some greenish shades can be obtained also from natural sources by double dyeing with blue and yellow, or also by using copper containing mordants and then dye with yellow giving plants. And here also are some embroideries of these Karelian folk costumes. I wanted to show here a little bit of the textile producing processes, as when we look especially dyeing, it was one stage during the textile processing, and in traditional dyeing, the yellows were dyed in the early summer, spring and early summer. So from plants we can obtain yellow color in early summer months. Then dyeing reds was done during the mature summer or early autumn in August. The red colors were stored in the roots of these madder plants, and they contained the most amount of dyes when they were collected in end of July or in August. And then blue was usually a bought ingredient from shops or color and dealers, and therefore the dyeing of blue could be done after the growing season in the fields, so in September, October. And in the winter months were reserved for spinning and weaving, and then early spring for bleaching fabrics on snow. But what we have done, we have tried to create, or we wanted to create Nordic color palette. And in Finland, we have this kind of dyers guild, which includes enthusiast dyers and dye professionals. There are about, I think, 2,000 or 3,000 participants in the Facebook. So we invited the enthusiasts to send us 2 meters of yarn and a description how the yarn was dyed. And we thought that in this way we could get an idea what plants are used for dyeing and what kind of color palette can be created. So altogether we had 300 pieces of yarn. Some of them were from these craft enthusiasts, but also we obtained one collection of dyer from Finland from 1917s, 1990s. She had dyed these yarns, and also my students at the University of Helsinki donated their samples, and of course our own samples. So we collected and reframed the research data. We left out such samples that didn't include description of the dyeing process, or they were dyed with two species. So we wanted only such samples that were dyed with one particular plant. And then we measured the color as CLAP values. So this is this kind of small machine that sends the light, normal light, to the surface, and then it measures the reflectance spectrum of the spot, and it creates this three-dimensional measures, where L means the lightness. It goes from 0 to 100, and the closer to 100 the L value is, the lighter the fabric is. A means the red-green axis. So if the A is very positive, like A is +20, this means that this is very red. If it's minus A -20, it's green. B is yellow, blue. If the B value is plus something, it's yellow, and if it's minus something, it's blue. And with these three values, we can describe different colors. We also did then some clustering with these codes and tried to create like clusters like yellow, red, brown. So we could see from what plant we could create brown color, from what plant yellow color, and so forth. And then we also tested the color fastness according to this standard, international textile standard, to see how light fast these natural dyes are. So this is our first Nordic color palette. So through this clustering, we created red colors, and in this Finnish collection, we obtained the most reddish color through these Cortinarius sanguineus and Cortinarius semisanguineus mushrooms. I don't know if these are used also in Estonia in dyeing, but in Finland these mushrooms are very popular and very easy to find. And we can also see that aluminium alum mordant was used, mostly 10% from the weight of the fiber. Here we can, what is interesting is that with madder, more like orange color was obtained in this group of samples that we had. Then kind of like yellowish or yellow greenish color we can get with tansy, meadowsweet, and some other quite like soft plants, soft green plants. And then with green, we can get from nettle, goldenrod, birch, or again fungi, this velvet roll rim fungi. This is not very we could improve our clustering program because, for example, this morsinko, this vote color is grouped together with these green colors. So this is still kind of under development how these different groups were formed, but it gives us somehow understanding what kind of colors can be obtained. And if we look at these brown colors, there are a lot of tannins and barks from trees and onion skins. And this is another kind of layout of these colors. But anyway, if you are interested, we have published this information in Biocolor Library, a database. It was launched at about a year ago. And here is maybe the easiest way is to go to biocolor.fi webpage, and there you can see the Biocolor Library, and it will lead you to this space. You can find information of plants, what kind of chemical structures are in these plants to create color. And then there is also a lot of these color swatches that you can also search according to these LAB or RGB codes, and then by plant name or a color you want to create. And it gives then some kind of estimation of the nearest colors in our sample collection for you, and you can also have the plant name and the mordant used for this color. Of course, for this color part, it's always depending on the material. So these samples are mostly wool, some might be linen or cotton, but they are not absolute colors, but they can give an idea what kind of colorants can be obtained. Then in our research, let's go back to the future's visions for our research. We have tried to create, and we wanted to show that like Pantone creates the color for each year. So in 2021, this was Ultimate Gray and Illuminating Yellow, and we created this Salix caprea from Willow Bark, this gray, and from Yellow Onion, this yellow, to show that nice colors can be obtained from natural, or to show what kind of colorants we can get from nature. And in these Pantone colors, anyway, we see that there is a call back to the nature, as in 2023 they have this Viva Magenta color, which they said that is based on carminic acid. So we are rooted in nature and we want towards sustainability. We have a lot of biomaterials already in use, and these and other degradable products, to which we would like to also use degradable colorants, and not such that would stay for a long time or not degrade at all. Also, circular economy is something that we should think more and more when creating artifacts. Utilization of low-value side stream, and then thinking of sustainability, efficiency, and purity in all processes. So not only thinking about the end product, but how we can create just systems that create no waste, so that everything could be used somehow or recycled, and also how we can create value from waste materials. I see that my time is kind of going to the end, so we want to pull away from fossil resources and also create processes which use low energy and low water consumption. And this is a little bit for the synthetic dyes, but with natural colorants also it's possible to improve the fibers and fiber materials, improve the dyes, and improve the coloration processes. So there are 3 different steps actually into which you can put effort and improve the system and create sustainable coloration. And if we think of dyeing, this uses a lot of energy and water, so mass coloration, supercritical carbon dioxide dyeing, and printing already creates less and uses less resources and creates less effluents. And this is one example also here in our Colour4CRAFTS process. University of Leeds has used so little dyeing vessel with carbon dioxide in, and it creates dry textile, and natural dyes completely dye the fibers. And we can also decrease the water solubility so that the dyes are more readily soluble for CO2, and we get better dyeing for CO2. Carboxylic acid groups in natural compounds create acid dyes readily to use without any mordant, and creates similar color values and also color fastness as the synthetic counterparts. Printing is also good technique. It uses less dyes and less waste. And this is an example with nettle of this zero waste process, where a company in Finland grows nettle. Leaves goes to food, stems contain fibers, and through retting we can obtain colorful liquor, which we can use for dyeing these colors, and then we can also use the leftover water for fertilizing. And we have used a lot of different natural sources, and with different dyeing techniques we have an understanding that some sources give very pure color fastness, while other sources very good light fastness and color fastness. So then for the applications we can choose such sources which give good color fastness for textiles. This I will skip. Only I mentioned that of course it's also possible then to develop the microbes further and cultivate them in this kind of cultivation tanks, in liquids with some nutritions, and then we can extract the dyes. And these kind of systems are already used for many drugs like insulin, but it's also possibility for dyes. And this is a very kind of a research area that is going forward currently very fast. Natural dyes have also use in other sectors as drugs. I already mentioned many of them have medicinal properties. They can be semiconductors and used in solar cells. Also, this kind of natural color craft tourism and learning is important in this sector. And here I wanted to give at the end one example from Finland. We have the first company, Natural Indigo Finland, that is producing the natural, the color plant woad that grows for 2 years. So first year you get the leaves and you get the blue pigment from the leaves. This company has made collaboration with Marimekko, for example, and with other companies with this blue color. The second year they get it blooms, the plant blooms, and they collaborate with bee farmers, and they get this woad honey. And of course they get then seeds, and they press seed oil, woad oil out of the seeds. And finally they dig out the roots of the woad, and this they sell to America for organic medicine. So a lot of different utilization. And just for you to know, if you are interested, in 2024 we had this Biocolors conference in Helsinki, and this conference is coming in 2028 in Vienna, Austria. And if you follow, for example, this Biocolor web pages or Instagram, we will inform of the coming events through those channels. And then about the books I already mentioned, coming soon is coming this Natural Dyes in Design and Color Education that we are developing now in this Colour4CRAFTS projects. It's an open access book, and we will give information about that in our web pages, Colour4CRAFTS web pages and Instagram. And also Dyes from Nature, if you know any Finnish, it's open access in Finnish from the University of Helsinki, and this English Dyes from Nature can be bought from Archetype Publications. And then the third book, this Biocolors Sustainable Stories from Nature, Lab and Industry, we wrote within the Biocolor project, and it's open access from the Aalto University web pages. The link is there. So thank you very much. So if you have...
Yeah, thank you, Riikka, for this broad overview. Unfortunately, the time is so limited, and you had to skip the interesting slides. But do you have any questions, Riikka? No questions.
I have
one question.
Is it possible to explain chemically how the color attaches to the cloth? I wasn't unfortunately from the beginning. Maybe you already explained it, but is there like a chemical process explanation, like how it is done?
Yes. Yes, of course, it depends on what is the fiber material, what the connections are. But if it's, for example, wool, which dyes best with natural dyes, so wool is a protein fiber and it has positive groups in chemical groups. These amino groups, and then natural dyes are usually in water environment negatively charged, and therefore these positively charged fiber groups and negatively charged dyes are attached to each other through these ionic bonds. Then if we use mordants, the mordants are positively charged ions in water. We usually pre-mordant the fiber, and in wool also there are negative carboxylic acid groups, and to this ionic negatively charged carboxylic acid groups, the positively charged ions like alum. In alum there is aluminium attaches, and then to this positive aluminium then attaches the negative natural dye, and this creates metal complex, and metal complex this chemical bond, and it depends on the now the mic is on. Sorry, this is echoing. Okay. Now it's better. If we use iron, then the forces that iron can produce are stronger than those forces that aluminium can produce, and therefore the light fastness properties of the fabric dyed with iron mordant are better than those that of the fabric that has been mordanted with alum. And naturally, of course, then with cotton or linen, then this is cellulose, and cellulose is negatively charged, and therefore the interactions between negatively charged fibers and negatively charged natural dyes is like repulsive, and therefore the dyeing result with the cotton and linen fabrics are usually less intense compared to wool. And wool is also very porous fabric, therefore there is lots of spaces and holes where these natural dyes can attach in the fiber.
Thank you. It was so interesting.
Thanks.